today, and we are going to talk about the phase diagrams of single component materials. So before we get started, let's kind of again recap some basics of phase diagrams. So phase diagrams are intended to illustrate essentially the phases of the system at equilibrium as a function of two or more thermodynamic variables. So those can be again, temperature, pressure, composition. So in the single component phase, we're going to look at our temperature as a function of pressure. Oops. Let's get my pen right here. There we go. Temperature as a function of pressure. So other times when we get into multi-component phase diagrams, we're going to be looking at temperature as a function of concentration X. But anyways, that's more detailed next video. So phase diagrams are very, very useful because they're going to obey the laws of thermodynamics. And so there are constraints on essentially how we could develop and draw and the structure of the phase diagrams. And they have to follow certain rules, specifically the Gibbs phase rule. So we are going to actually figure out how many degrees of freedom we have in a system and what are kind of the rules and constraints on how our phase diagram looks. And that's given by this Gibbs phase rule. So the Gibbs phase rule is very, very, very important. It tells us how many phases can be in equilibrium simultaneously. And when those phases are stable along essentially a line, basically a field, so basically 2 degrees of freedom, a line, 1 degree of freedom, or point, 0 degrees of freedom. Again, we'll get into that in just a second. So the criteria, in order to kind of satisfy the Gibbs phase rule, we have 2 criteria for phases to be in equilibrium, basically at a given constant temperature and pressure. And one of those criteria, the first one for the Gibbs phase rule, is that the chemical potential of each component must be equal to each other in each phase. So the chemical potential of each component must be equal in each phase. So I have components. So my component is 1, 2, and then C here. So component 1, 2, C. The phases, P, phases are alpha, beta, gamma, P. So those are my different phases here. And the chemical potential is also defined basically the change dG, dN. Basically, this is the number of basically moles or molecules at a constant, actually, when you ever see this as a constant temperature and pressure. So we take this derivative as a function of at a constant temperature and pressure. So that is kind of the first criteria that gives free energy, is that we need to be in equilibrium for multiple phases to be in equilibrium at a given constant temperature and pressure. We need the chemical equilibrium, the chemical potential, the chemical potentials to be equal to one another. So that's kind of the key idea. The chemical potentials of each component, each phase must be equal. So this leaves us with a number of equations that we have to kind of satisfy. So we actually end up with this C times P minus 1 equations. Why? Because we have C components, so C components, and P minus 1 because, again, we have to have this equal to this, this equal to this, so we end up with 1 minus 1. You can do the math there. Now, the second condition that we have to consider is given by the Gibbs-Duhem equation. And this is essentially that dG is equal to VdP minus SdT, minus our sum of our chemical potentials, I is 1, to our number of our components, number of molecules here, and I in a certain phase. Again, you kind of just write this more generally, d equal to 0. So in order to also be in equilibrium, for phases to be in equilibrium, we need our Gibbs free energy to be minimized. So that's kind of all that it's saying here. So we need, in each phase, we need to be basically at equilibrium. It needs to be the lowest energy state. So to be in this alpha state, to be in the beta state, we need to kind of have this lowest free energy. So then here, we're just dealing with not components necessarily, even though the components are in here. We're just dealing with P equations. So P equations here. So now our degrees of freedom is going to be essentially total number of variables minus the total number of equations that we have. So the total number of equations is this, C times P minus 1 plus P number of equations. And the number of our variables is C, number of components, times the phases. That's what we're kind of dealing with. We're dealing with C and P. How many components do we have? How many phases do we have? Now, this too comes into play because we can also vary temperature and pressure as our independent variables. So number of variables minus number of equations gives us this beautiful equation. Actually, I'm going to erase right here. This beautiful expression here. And we can kind of rearrange this. It's kind of more often shown as D plus P equals C plus 2. And this is for very, very, very important. So this is very, very important. This is for a single component. component temperature versus pressure phase diagram. So this is awesome, but let's go ahead and let's do a couple examples and let's see, put this Gibbs phase rule into action. So let's go ahead and shift over here. I'm going to go. So let's look and let's calculate the degrees of freedom. So P plus P equals C plus 2. So what are the number of components in this system? Well, it's a single component phase diagram, so C is going to be always equal to 1. So at this X, we know how many phases are we in. We're just in the liquid phase. So it's D equals 1 minus 1 plus 2. So we are left with 2 degrees of freedom. What does that mean? It means I could vary either I could move here, temperature, and I could move pressure independently. So I could move in T and I could be unconstrained in my pressure and still be in this liquid phase as long as I'm kind of at this location here. So I could vary temperature or pressure independently and still be in that same phase. What about this location 2? How many phases are we at now? Well, our number of phases is actually 2. We are in a liquid phase and a gas phase simultaneously along this line. So now, what's our degrees of freedom? It's 2, or actually minus 2, plus still 1 component. So we're still single component here, plus 2. So P is equal to 2, C is equal to 1 always. So this holds for every kind of problem here in this diagram. And now we are left with this expression right here, where our degrees of freedom are now 1. What does that mean? It means that if I change my temperature, for example, my pressure is fixed. So I need to kind of, if I want to, or simultaneously, if I want to reduce or change my pressure, my temperature is fixed. So I have to move along this line. So I can only vary one variable. If I vary temperature, then the pressure value is fixed in order to stay on this line. So let's do the last one. What's happening at 3? Well, my components is still equal to 1. What is my phases? Well, I'm solid, liquid, and gas, so my phases is actually 3. So D is equal to minus 3 plus 1 component plus 2 variables. Now my degrees of freedom is 0. I can't change temperature or pressure. And this special point where degrees of freedom is 0 is called an so that's an point on the phase diagram. So you can kind of go back through here and take a peek at these degrees of freedom and how do you kind of calculate that. But this is an invariant point. So next time we are going to look at a phase diagram, and actually we're going to look at this Clausius-Clapeyron equation and look at the slopes. So I'll see you next time.